Hello everybody, welcome to Embedded ARM Dev. In this video, I'm going to give you an introduction to compiling using GCC for Linux. So what exactly is compiling? So compiling is simply the process of converting some source code into low-level machine code for a specific processor architecture. It is important to remember that compiling is a multi-stage process involving multiple tools to create a final executable binary. The compilation process is generally broken down into 4 stages. They are preprocessing, compiling, assembling, and linking. The overall concepts of compiling presented in this video are applicable to compilers in general. However, in this video, all the tools, commands, and file types that I'll be talking about are specific to the GNU toolchain when you're compiling the C language for a Linux operating system. The first stage of the compilation process is preprocessing. In this stage, the macros and include files in the source code are expanded so that the source file contains everything it needs to be compiled. With GCC, the command cpp invokes the preprocessor. cpp takes a .c file as input and outputs an expanded source file with the extension .i. The .i file contains the source code with all macros and include files expanded. The second stage is the compiling stage. In this stage, the expanded source code is compiled into human-readable assembly code. Assembly language is human-readable processor instructions for a specific architecture like ARM, x86, MIPS, etc. Passing the S option to GCC will cause the compiler to stop after compiling to assembly and not continue with the rest of the compilation process. The output file contains architecture-specific assembly code. The third stage is the assembly stage. In this stage, the assembly code from the previous stage is assembled into an object file that contains machine code that is readable by a specific processor architecture. The assembler is invoked by the AS command. The assembler takes a .s file with the assembly instructions as input and creates an output file with the architecture-specific machine code. The fourth stage is the linking stage. The linker is responsible for linking object files together to create the final object file. For each .c source file, there will be a corresponding object file. Most programs are composed of many object files. They must be linked together into a single object file. Compiled objects will contain references to functions or data that exist inside other objects. It is the job of the linker to link these symbols from other object files and external libraries together to create a single object file. A symbol is simply a reference to a component of an object like a function or a variable. The symbol is eventually resolved to an address where that component is located in memory. The linker is invoked by the command ld. The linker takes object files as input and outputs a single linked object file. Now, there are 2 types of linking, dynamic linking and static linking. With dynamic linking, if the executable uses functions from some external object, like a shared library, for example libc, then the compiler creates references in the executable to those symbols. When the binary is loaded into memory and becomes a process, the symbols for those external libraries are resolved by the dynamic linker or loader. So the compiled executable does not contain the actual code for those functions that exist in the shared libraries. Now with static linking, all of the symbols are resolved at compile time and they are compiled into the final object file. So a statically linked file contains all of the code it needs to execute. To create a statically linked executable, use the static option with GCC. So what exactly are object files? So the GCC compiler will create 3 types of object files: relocatable, executable, and shared objects. A relocatable file is just the output of the assembler stage of the compilation process. It is not an executable file and needs to be relocated into another object file by the linker. An executable object is simply one that can be executed or run. A shared object is just a shared library. It is not executable and is designed to reside on the target system so the dynamic linker can link into it when executable files on the system need it. On Linux, object files are in the form of an executable and linkable format, or simply the ELF file. So now let's talk about GCC and some of its commands and options. So it's important to note that the GCC command invokes all 4 stages of the compilation process. You don't need to individually call the preprocessor, the assembler, and the linker. So the basic command is GCC followed by the source file, and with the O option you can specify the output file. So here are some other options we can use with GCC. As I said earlier, the O option sets the name of the output file. The capital E tells the compiler to stop immediately after the preprocessing stage and not to run the compiler. This would result in .i files, which are just preprocessed files. The capital S option tells the compiler to stop after the compilation proper and not to assemble. This would result in .s files that contain assembly instructions. The lowercase c option is used to compile or assemble the source files but not to link them. This would result in object files that are relocatable. The save temps option tells the compiler not to delete the intermediate files, such as the .i, .s, and .o files. This is useful if you want to inspect these files after the compiler is done. So the capital I option tells GCC where the non-standard directories are to search for and include files. So for your project, if you have header files that are not in the standard directories, you need to specify these directories so that the project knows where to find them. You can use the lowercase l option to specify a specific library name that you want to link into. By convention, GCC uses library names that start with lib followed by the name of the library. If your program is using any functions from these libraries, then you need to make sure to link it in using the lowercase l option, otherwise the linker will throw an error. The one thing I would like to point out though is that when you're using libc with the GCC compiler, you don't have to pass in the linker option -lc to specify linking with the standard library. GCC just figures it out. However, if you're using other libraries like math library or pthreads or any other libraries, you do need to use the lowercase l option followed by the name of the library. So now we're going to do some practical demonstrations to reinforce some of what we learned. Okay, so right now I'm on my Ubuntu Linux VM and I've created a little projects directory here and I've created an example 01. And in this directory I have a very basic source file and I'm just going to use gedit to show you what's in here. Okay, so let's make that a little bit smaller. So this is a very simple file, a very simple program. So I wrote this program specifically to require linking into two shared libraries, the libc library and the math library. So here we have the standard, printf call hello world, and this will require linking into libc. And then right here, these three lines are just to create a random number. All I want to do is create a random number right here. This rnum is the end result of these three lines. Okay. The reason I want to do that is because I want to feed a random number into the square root function. All right. The square root function is what will require linking into the math library. Okay. So if you were to just pass in a hard-coded number, like you're like, well, what is the square root of 26.2? So the problem is GCC, when it compiles this, it wouldn't actually link into the math library because this is a constant, right? As far as the compiler is concerned, this is a constant, so it would just assign this value to SR, and we would never call into the math library. Okay, so I had to create some way of dynamically creating, at runtime, creating a random variable. So that's all this is right here. Okay, so the include files, the standard input/output is for printf. Okay, math, of course, is for the square root. Standard lib, I believe, is where the random comes from, and then the time.h is, of course, used for this time t. Okay, the type time t. All right. Okay, so I'm just going to close that out. Go ahead and list again so we see that we have the source here. So we're just going to invoke the compiler. We're going to pass it hello.c and make the output hello. Okay. Now, this is going to complain because undefined reference to square root. Okay. This is because the square root function requires us to link into the math library, and we didn't tell the compiler to link into the math library, so it gets confused. The linker, LD, returned 1 as an exit status saying it's an error. Okay, so we need to tell the compiler, hey, let's link in the math library. So to do this, we have to use the lowercase l option. So there's the source file. So I'm going to link in math with the output hello, and this should work and not complain. All right, so we'll do a list, and there we go. So before we get into that, I want to point out that this option right here where you specify the library that you're linking in, this needs to come after all of the source files that link into it, that require it. Okay, so if I were to do this, right, then it'll fail because hello C will not get linked in because the linker command gets called before it gets built, and so it should throw an error when I do this. Okay, same thing before, right? Because we have it in the wrong. So the order where this appears is important. So you want to make sure that it appears after any source files or object files that need it. Okay. All right. So let me clear our screen so we have a thing. Okay. So I need to rerun this again because it wiped out my target. Okay. So this is the right order. Okay. All right. So there it is again. So we'll just go ahead and run this. All right. So it says hello world, and it's the square root of this random number is the square root of that random number. Okay, so it works. If I were to run it again, it should give me another random number. Okay. All right, so the first thing I'm going to do is I'm going to use the file command to give us some information about this particular binary. Okay. So when we list it, this gives us some pretty useful information about this. So it tells us that it's an ELF, an executable and linkable format, that it is for a 64-bit processor. The LSB means least significant byte. Okay, the other possibility would be most significant byte, MSB. So LSB means that it is Little Endian, and MSB would mean that it is Big Endian. Okay, and so this shared object here is a little misleading because actually on Linux, the default for GCC is to compile the executables as what's called position independent executable, PIE, which means that the binary could get loaded into any memory address and it would run fine. So when the compiler creates it, when it compiles it, it creates it as a shared object. Okay, so normally we would expect it to say executable right here. So what we can do actually, if we want to force it to do that, is we can pass it the no PIE option. Okay, and that should do it. Okay, it didn't complain, so let's do it again. All right, so there we go. So this is what, so now we have, these are all the same, okay, ELF 64-bit, Little Endian, and now it shows it as an executable, okay. So the next thing it shows is the processor type, so I'm running on an x86. This is the EABI version, okay, we won't worry about that too much right now. One thing that's really important is this right here. It says that it's dynamically linked. That means that the binary, it has references to external symbols that exist in shared libraries somewhere, okay? So that means that you're going to have to depend on shared objects existing on the target system. All right, and so here, this is the interpreter that the program is going to look for on the target system. The interpreter is the linker and loader, okay? This right here is what it's going to look for on the target system in order to run, okay? If this doesn't exist, then the executable probably will not run. So next thing is you got the SHA ID of this build, okay? That's a SHA-1 of the target, the object. So if we ran it again, you would get the same thing. So if I ran the compiler again, we should get the same number. Okay, so it's the same number, right? Okay, and then this is for GNU Linux. It gives you the version of the GNU there, and then not stripped. So we'll get into that a little bit more later, but that essentially means it has a bunch of symbols in it that help with debugging, and these symbols take up a lot of space actually in the binary. And so before we would send this out, distribute this binary, we would actually strip it to take all that symbol information because it's not necessary for the program to run. It's usually only useful for debugging. So now I'm going to show you a utility that comes with bin utils, which we'll talk about in another video, called readelf. Okay, so readelf is a program that will read and parse metadata about ELF files. Okay, it's very powerful, has lots of options. If you pass it the TAC A, the A option, it'll list everything. So if I do that, you'll see it stream out a whole bunch of stuff. Okay, this is all sorts of information that's very useful for analyzing the binary. Okay, so one thing that's pretty useful is we can do that, and I'm looking for a certain term, shared. Okay, so I'm calling readelf. I'm having it list everything. I'm calling it on the binary hello, I'm piping it to grep and looking for the search term shared. Okay, so what this gives us is these two libraries. Okay, so when the linker loads this binary into memory and it becomes a process, then it would read these and say, oh, okay, this process, this program needs to link into libc and it needs to link into the math library. Okay, so the linker would be responsible for loading those into memory if they didn't already, which they probably are already loaded into memory. But if they weren't, then they would get loaded into memory, and the linker would resolve all of the references to like printf and square root and all that stuff that it needs. Okay, so this is one way you can look at a binary and know exactly what shared objects it needs, what shared libraries does it link into. So these two right here need to exist on the system where this binary is going to run. If they don't exist, then the binary won't run. Okay. And so another thing I want to show you here is we do the same thing, but instead of searching for shared, we look for interpreter. Okay. So again, this gives us the same information that the file command did. This right here is the linker/loader that this binary is going to expect to find on the system. Okay. So if it can't find this, then it won't run. All right, so the next thing I want to do is I want to recompile this. Okay, so we're going to do hello.c, link into math, and I'm going to do no PIE again. Okay, and then I'm going to do the save temps option. Okay, and output as hello. So, okay, that looks right. Okay, so what this did, the save temps option kept all the temporary files. So this is the result of the preprocessor stage with all the expanded source code. This is the result of this one is the result of the compile stage. So this is actually compiles the I file into assembly. And then here, this is an object file. And this contains, so the object file is machine readable code, which was compiled from the ARM assembly. Okay, so first thing we'll just look at hello.i. Okay, and then it's just C source code. Okay, identifies it as C source code. And if I do hello.s, it identifies it as assembler source. And if I do hello.o, we see that this is a 64-bit LSB relocatable. So that means this is not executable. If I try to run this, hello.o right here, it won't work. Okay. It says permission denied, but it wouldn't even run it if I tried to. Okay. So let's take a look at these. Okay. First, we'll take a look at okay, we use gedit so it's easier to scroll around. Okay, so this is, first let's look at, okay. So we got the source file here. All right, so we've got all these include files, and I don't actually have any macros, but if I had a macro like, define mathpy 3.14, something like that, right? And then somewhere in here I use that, right? I would say double pi equals mathpy. I don't know, something like that, right? So this would every time it sees this math pi, it would replace it with 3.14. Okay, so this right here would actually say 3.14. Okay, so this is the, you know, macro, a defined constant, and it gets expanded in this file. Of course, I didn't include that in the original, so you won't see it, but there you go. So this is actually a lot of stuff. It's not, in my experience, too useful to look at this file, but if you need to, you know how to do it. All right, the next one that we should look at is the assembly. Okay, so this is hello world compiled into assembly. Now this is x86. Okay. All right. So if you're not familiar with assembly, this probably looks very weird. But one thing you notice is that here there's a call to square root. Okay, so in this binary, when it actually compiles it in the object file, this square root will not be part of this file. Okay, it calls, this is a reference to square root, which is going to be somewhere in shared memory on the system. Okay, and up here we see a couple others. So we have, this one is a little bit interesting, puts. So actually, because in our source code we do printf, apparently it didn't need, I'm sorry, this one right here. Okay, this one right here, because we didn't pass any format specifiers, this one was simple enough that it can call puts. Okay, but later down here it actually needs the full printf function because I passed in these format specifiers here. Okay, so that's why there's two of them in there. All right, so you can see here that's the first printf. This corresponds to the time function, okay, which is this call right here. Okay, passing in t and getting it, it's initializing this with the current time. All right, then you've got srand and rand both get called. Okay, so srand is right here, and then so this actually, in case you're curious, this right here seeds the random number generator. Okay, srand. So when we take the time, so every time we run this, obviously it's going to be a different time, and that seeds the random number generator so that this number is semi-random, pseudo-random. Okay. So anyway, that's what this does. All right, and so you can see those calls in here, and none of this code is going to exist in this object file. Okay, it's just going to these are references to where it's actually linked to. It's eventually going to get linked in by the dynamic linker, and of course here you can see the call to square root. Okay, PLT stands for procedure linkage table. That is something we're going to get into in another video. That's a little complicated, but that's how the linker will resolve it at runtime where this is in memory. Okay, all right, so that's good. And then we'll look at, I think I already looked at this, but, right, so this, yeah, we did look at this. So this is relocatable, and that's the object file. So it wouldn't do any good to look at it in gedit because it's just object code. Right, it's just, random. This is not something, some of it's readable, but a lot of it isn't. Okay, but this is an elf file, so we can use readelf. Sorry, we'll use a, and we'll pass it hello.o. Okay, so we can use readelf to get a bunch of information about it. Okay, all right, so what we're going to do now, let me see if I can get rid of these by just running the compiler again. Okay, so just going to get rid of these. Let's see if I can get rid of those intermediate files. Nope, didn't. So we're going to remove hello.i. Okay, they're just cluttering up. All right. So next thing we're going to do is compile it statically. So what this is going to do is create an executable that doesn't link into any external libraries dynamically. All of the functions, everything that it needs gets compiled into the executable object, and so it can run by itself. It doesn't need to link into anything. Okay, so in order to do that, we just passed it the static option. So this is the same as what I did earlier. We're invoking GCC. Source is hello.c. We're linking into the math library. We're going to do non-position independent executable. However, when you actually compile a program on Linux, I would say just leave this out and let it compile it how it wants to. So we're going to say static, and we're going to call the output static. Okay, I want to keep the original dynamically linked one. All right. So did that work? All right. So I'm going to list all. So one thing I want you to notice here is the size of the hello. This is the same program. Okay, they do the same thing. But this one is dynamically linked and this one's statically linked. So you can see that this is significantly larger than this one. Okay, that's because all of the code that it needs, everything it needs, is inside of it. It can run. So if I run hello or hello static, okay, it does the same thing. Obviously, it gets a different random number each time, but it does the same thing. All right. So if I list file on the static one, okay, it gives us the same information. It's executable x86-64 until we get to here, and we see that it's statically linked. Okay, so we could run this on any x86 that's running Linux with this EABI, and it wouldn't need to link into libc or libm. Okay, so if earlier we did the readelf, and we got to pass it to this. So I'm going to do hello. First we'll do hello. Remember how this one showed this shared library? So this is so this is the original dynamically linked one. Okay, and so what I'm going to do here is do the static, and you'll see that there's nothing. It doesn't need anything. Okay, and again we'll look for the interpreter, and it doesn't need anything either, right? If we do that for the original dynamically linked one, then it tells us that it needs this interpreter. Okay, so since it's not dynamically linked, it doesn't need the dynamic linker at runtime, and so it can just run completely by itself. All right, another thing I wanted to show you is a couple of the GCC options. So I talked about them earlier in the video, and we're going to go over two of them real quick. So, okay, so if I do this and I do the capital S, what that does is it stops after the compile phase. So what you'll get is just an assembly file. Okay, so this would be a good way if you're just like, well, I just want to see what the assembly is going to look like. What kind of assembly is this going to make? Okay, so again, we looked at the assembly earlier. Okay, so this is what the assembly code would look like. All right, so if I was to remove hello, so now that binary is gone. I'll go ahead and remove hello static. So we just have the source code. Okay, so if I call the compiler, pass it S, and just give it, okay, there. What you see here, there's no binary, there's nothing else, it's just hello.s, which has the assembly file. Okay. So another one that one's not that used that often. Use that if you want to maybe look at the assembly, maybe to see if you can spot a bug, or maybe it's doing some kind of optimization that you don't want it to, or you might be able to look at it to see if it's doing what you actually want it to do. There's many reasons to look at the assembly. Okay, but another common option is the C option. Okay, and so you pass it the C option. What it does is it stops after the assembly phase, the assembly stage, which results in a relocatable object file. Okay, so it doesn't link it. That's basically what it does. It does everything but links it together. So if I do that, then we get the hello.object file. Okay, and so if I file, okay, then we see that it's relocatable. All right, so you'll actually see this a lot when you use makefiles. Okay, the TAC-C option, because a lot of makefiles, they want to build these intermediate object files, but they don't want to link them until a later time. So they'll build them, and then they'll link them together when they need to. Alright, so that's it for practical demonstrations. So now let's summarize what we've learned in this video. So we talked generally about the compilation process, and it's made up of 4 stages: the preprocessing stage, compiling stage, assembling, and linking. Remember that GCC handles the entire process. There's no need to individually call all the intermediate commands. Okay? If you do want to keep the intermediate files for inspection, then use the Save Temps option, which will prevent GCC from removing those intermediate files when it's done with them. And that's it for this video. I hope you found this video useful. Thanks for watching, and we'll see you in the next video.